All right, let's establish some algebraic properties of limits. So just like we did in the previous video, we're going to throw out some disclaimers here about what these values are going to be defined as. Let's let B and C be real numbers. Let's let N be a positive integer. And let's let F and G be functions where the following statements are going to be true. That the limit as x approaches c of f of x is some value L, and that's our limit notation that we learned back in topic 1.2, that this limit as x approaches c is equal to L for f of x. And let's let the limit as x approaches c of g of x equal, we'll note it with capital M because we might be talking about a different value here since it's a different function. But notice that we're talking about as x is approaching the same value, whatever c is, which is just going to be defined as a real number here. So let's say that these two statements are true for these two functions, f and g. We have some properties that are going to be very nice when it comes to evaluating limits. The first property that we have to look at is called the scalar multiple property. And what it says that if I have the limit as x approaches c of b times f of x. In other words, I'm taking whatever f of x is and I'm multiplying it by a multiple b, which we defined as a real number. Then what this equals, what this scalar multiple property says is I can take this this multiple b and I can move it outside of the limit, and I can say that this is equal to b times the limit as x approaches c of f of x. And if you look at what happens here, this right here we already said was equal to L, so this equals b times L. So what you can see here is that the b came out and I was left with what we have already said is equal to L. So a multiple can come out when it comes to limits. The next thing I want to look at is my sum and difference property. And this is where I'm going to incorporate both my functions f and g. What this says is that if I have the limit as x approaches c of the sum or difference of two functions, so I'm going to have f of x plus or minus g of x, what this says is that the limit of this sum can be expressed as the sum of the limits. So I can express this as the limit as x approaches c of f of x, plus or minus, I should have said sum or difference just a moment ago, plus or minus the limit as x approaches c of g of x. And again, we have these defined for us. This is defined as L, and this is defined as m. So that equals L plus or minus m. We also can do products. And this is actually really powerful. And I'll tell you, in calculus, a lot of times sums and differences are going to behave the way we kind of want them to. Products and quotients don't always, but they do for limits, which is a very, very nice thing. If I have the limit as x approaches c of the product of two functions, f of x times g of x, well, what that says is that the limit of this product ends up equaling the product of the limits, the limit as x approaches c of f of x times the limit as x approaches c of g of x. And again, we have these values defined as L and m, and so this equals L times m. Likewise with quotients, we're going to be able to split them up the way we would like to. So the quotient property for limits says that the limit as x approaches c of the quotient of two functions is equal to f of x, let's say the quotient f of x divided by g of x. The limit of this quotient is going to be the quotient of the limits So this equals the limit as x approaches c of f of x divided by the limit as x approaches c of g of x. And again, we have those two things defined for us. This is L divided by M. And of course, whenever we talk about a quotient, we should really make sure that we say that that's going to be true so long as M is not equal to 0. If M is equal to 0, then we're going to have an issue where that limit probably is going to be undefined and would not exist. So make sure that the value for M doesn't end up equaling 0. All right, those are 4 of the properties. The last one that we're going to really look at is going to be the power property. And this says that the limit as x approaches c of f of x raised to the n power. So if I have a function and I raise it to the n power, that this limit notation can actually carry inside, and we can say that equals the limit as x approaches c of f of x raised to the n power. This we have defined as L, and so L is raised to the n power. And remember earlier we threw in the caveat that n has to be a positive integer in order to guarantee that this works. And I know that maybe this notation looks a little bit confusing, and it's a lot to have thrown at you in one moment here. The bottom line with a lot of these properties, when we start evaluating limits algebraically, these are going to be the properties that are going to let you do what you're going to want to do when we start evaluating limits. Limits, very fortunately, work very intuitively, and you'll see that when we actually start working some examples in the next video. That these properties right here, even though this notation may look like a lot to have thrown at you in your first week or two of calculus, these properties really are going to be very powerful, and they are your friends, not your enemies, as you'll see here in a little bit. There's one last thing that I want to make sure that we add here in this video, and that's going to be looking at the limits of composite functions. For composite functions, where the limit as x approaches c of g of x is equal to L. So whatever the g of x, as I get close to c, if I'm approaching L, and then let's say the limit as x is approaching L of f of x, as long as that equals f of L, which is what we've seen in a lot of very intuitive functions, then what this means when we do composite limits, the limit as x approaches c of the composite function f of g of x, what this equals is I can take this limit as x approaches c, and I'm going to apply it to this innermost function g of x first. This equals f of the limit as x approaches c of g of x, which we've already said is equal to L, and so this equals f of L. And I don't want to harp on this too much because the notation for this one can be kind of particular. We'll look at an example on the next video of how this applies to composite functions. So we'll get this right in the next video. The main thing I really want you to take away are these 5 properties right here, because they're going to be very, very important when we want to go evaluate limits directly and then using some of our algebraic techniques.